Okay, welcome everybody. It's a great pleasure to have with us Nikolaos who's going to present MSc Thesis. We're going to start with a very small story so that you know a little bit of background about the thesis. So Nick is an undergrad here at our department and he was already published author very early on in Milli-lensing. And then as he was approaching like graduation, something wonderful happened. We were extremely lucky that the magnificent Carolina Casadio decided to apply for an ERC to seek milli-lenses with the API and use them to probe dark matter clouds and bring this fantastic work to the Institute of Physics here in Crete. So she submitted her proposal. She did very well. Went to the second round, and she had to give an interview. See? And for her proposal, she had made a calculation that was very simple, very basic, based on all dark matter, how many milli-lensing she expected to detect with this program, if you know standard cold dark matter. And the concern was, as she was preparing for the interview, what if she gets challenged and asked, okay, but can you use really this program to discriminate? What happens if dark matter got cold, warm, if it's set up? Will you see a difference in the number of lenses that you probe in your program to actually make progress? So we thought somebody has to calculate this just so that she's prepared. And here comes Nick, because when you have a high stakes problem, you go to Nick. And so we presented him with this problem and the tools, and indeed, you know, it's not a lot of time between the round and the interview. So this also had to be done fast. Right? So in the summer between, it might have been graduation, like masters or the previous summer. Anyway, in the summer, Nick finishes this work. So the plots are ready. Carolina goes to the interview, and then she's asked exactly that. She has returned. Here is the answer. Fantastic. Carolina gets the ERC. We have this wonderful project here. We're so happy. That's Nick's master's thesis. And of course, as you might imagine, I use this story shamelessly in every reference letter I write for Nick. Which brings me to the next part of my storytelling. So now Nick is about to graduate. If we decide he good, and in that application he will be continuing his studies at the PhD level at Princeton, which was the institution he selected from the several he had as he was applying. So without any further ado, Nick.
Okay, thank you, Professor Pavlidou, for this nice interview, and thank you all for coming today here. I'm going to talk to you about my master thesis, which I completed under the co-supervision of Professor Pavlidou and Dr. Casadio, and the title of my thesis is Discriminating Power of Milli-lensing Observations for Dark Matter Models. So as you can understand, we are going to talk about cosmology. So let's take a step back and go to 1915, when Einstein published his field theory of gravity. Back at that time, people thought that the universe is made of dust and radiation only. So the first cosmological models were models that didn't predict any static solution. But people like the simple case, so they wanted a static solution. They wanted a universe that is static, neither expanding nor contracting. So Einstein published a paper 2 years after the first one of general relativity, where he introduced this lambda constant, this cosmological constant, in order to obtain a static solution. And indeed, he did so. But in 1929, Hubble published some results where he plotted the velocity of nebula, of galaxies, the radial velocity, as a function of the distance, and he found a positive correlation. He found that as we go further from the observer, the radial velocity increases. So he provided the evidence in favor of the expansion of the universe. For that reason, Einstein abandoned the idea of the cosmological constant, but nowadays we know that this constant is responsible for the accelerating expansion of the universe. However, we have no clue about its origin. Apart from that, in 1913, people found evidence in favor of the existence of a new exotic form of matter called dark matter. Zwicky, in 1913, made some observations in the coma cluster, in the coma system, and by comparing the mass that he inferred from the velocity dispersions, the velocity dispersion of objects in the coma system, which is can be obtained through the Viral theorem, he found that this mass is 400 times larger than the one that we see, the luminous one. So he concluded that there must be a mass excess in this coma system that cannot be explained by the ordinary matter that we know. So he provided for the first time ever evidence in favor of dark matter. From there, since then, we have many other observations, independent observations of the existence of such a matter, and the most solid one, the most solid evidence that we have, comes from rotation curves in galaxies. From Newtonian theory and the Keplerian prediction, we expect the velocity squared to drop as 1 over r as we go away from the center of a galaxy. The y-axis is the velocity, and the x-axis is the distance. So we expect such a behavior as an asymptotic behavior. However, Rubin and her collaborators in 1980 plotted the rotation curves of 21 spiral galaxies, and they found that the rotation curves tends to be flat. So this reveals that there must be another form of matter, not the luminous one that could explain this one, that was predicted this one, but there is a mass excess that is, and the mass distribution of this matter is more extended, so that to make the rotation curves to be flat. So nowadays, the established model to describe the dark matter in the cosmology general is the lambda CDM paradigm, in which we have the cosmological constant that I talked to you at the beginning, and the form of dark matter called cold dark matter. We know that dark matter is a dominant component of matter in the universe, and we know, and according to the lambda CDM model, it consists of massive collisionless particles. The dark matter particles are thought to neither emit nor absorb radiation, and therefore they interact through gravity. Although the lambda CDM model has been successfully describing large-scale observation, it seems to fail when it comes to small-scale observation. For example, in this figure here, I show you the density as a function of radius for observational data and the lambda CDM theoretical prediction. The gray zone, the gray line here, is the prediction from cosmological simulations of a CDM model, while the data are the observational data in dwarf galaxies. Although the lambda CDM prediction predicts a steep power law-like density profile, and the density goes to infinity as we go closer to the center of a halo of a galaxy, it's not the case for observations. We see that the density tends to be constant. So it's like we have a core at the center of the galaxy, of the halo, the planet. So is it a core or a cusp? For that reason, this problem motivated people to propose some other dark matter model, some alternative, to explain the core, the existence of a core. They considered, what if we allow for dark matter particles to interact with each other, to exhibit self-interactions? They did so, and they ran some cosmological simulations, and they showed that if you allow them to interact, then because they exchange energies, the inner region of the dark matter halo gets thermalized, and therefore it pushes material a bit away and a bit further away, and smooths the core. So we get a core instead of a cusp, a divergence of the density profile at infinity. So in this figure here, I show you the density as a function of the radius. And as you can see, for the cold dark matter, we get this form, which declines to infinity as we go closer to the center. While if we allow for self-interaction, then we get a core. The density becomes constant as we approach the center of the halo. But apart from that, there is another lambda CDM challenge, which is the diversity problem. People plotted the data, the data of the rotation curves for different galaxies, spiral galaxies, and they found that in some of them, some data are in favor of a cusp. The velocity squared increases very rapidly with radius and then flattens out. While in some other, like this one or this one, it's much smoother, and actually these data are in favor, predict a core at the center. The dark matter halo to have a core at the center. So, however, the lambda CDM predictions from simulations show these bands here, which of course are inconsistent with data. For that reason, again, people get motivated and proposed again the self-interacting dark matter scenario to alleviate this problem. And indeed, they did so, and they found that they can fit very well all rotation curves, either if we have a cusp or if we have a core. I will not explain more about how this fits has been obtained because I don't have time, but we can discuss later. A third problem was the missing satellite problem, because according to the lambda to the structure formation theory, we expect the number density, the abundance of halos, as a function of the mass, to scale like this, to be a power law. So if you assign to each halo a galaxy, then you also expect the number density of galaxies to be similar to this, to the blue line here. However, the observed number density of galaxies exhibits a drop at low masses. People thought that this may be resolved if you introduce some abundance magic relations, but there are some another part of researchers who again get motivated to modify the properties of dark matter particles, and they proposed the warm dark matter-like scenarios, according to which we get a cutoff at low masses. The number density is suppressed. So, in order to explain you this figure, you can see that I have plotted, in order to show you the suppression, I used this plot of Hu et al, where the number density is plotted as a function of the mass, and we multiply by m squared just to make it a plot more decent. The black dust line is the cold dark matter prediction, while the colored lines are predictions for different warm dark matter or self-interacting dark matter models. The common thing between these models is that the rest mass of the dark matter particle is on the order of kV. This means that if we go back to the matter radiation equality epoch, then the velocity of the dark matter particles were not negligible, and therefore they could move fast and wash out any small scale perturbation or fluctuation in the density field that was there. And therefore, small scale fluctuations, small scale regions of overdense region could not collapse because of the free streaming. The particles were moving fast and washing out any density fluctuation, any density field that was different from the mean or the average matter density. So, as I have shown you, we already seen different dark matter models, so we come across an enigma. What is the nature of dark matter? There are many different models that fit well different parts of observations. And actually, the candidates are many, and we already talked about the cold dark matter, which is the standard one, the warm dark matter or the stellar neutrinos, which are similar to the warm dark matter particles, where we talked about the self-interacting, in which people propose to explain the core in density profiles. And there are other more exotic dark matter scenarios like the dark atoms, the fast dark matter, primordial black holes, etc. And actually, the dark matter tree looks like this. We have many dark matter models. So we need to find a way to discriminate between them and rule out some sets of these dark matter models. So how could we do that? How could we achieve that? One solution could be to study dark matter on galaxy cluster scales. However, at this scale, the number density, as I showed you earlier, is identical to the prediction of the CDM model, as it should be, because at large scales, we know that the lambda CDM is consistent with observations. Apart from that, the baryonic effects at these scales are important. Baryons play an important role in the mass distribution of dark matter inside a halo. And there are people that have tried to model the effect of baryons in the halo, in the dark matter, through the baryonic feedback models. But as I will show you now, people have run cosmological simulations to try to model the baryonic feedback. And as you can see in this video here, in which the Hamels project have run 5 different cosmological simulations using the same initial conditions. And the blue line, the blue color is the gas density, while the red one is the gas temperature. As you can see, although they start with the same initial conditions, the red color, which is associated to the gas temperature and therefore to the baryonic feedback, is different from simulation to simulation. So we cannot yet trust these models to model the baryonic effect on the dark matter halo and therefore subtract it and isolate the behavior, the properties of the dark matter halos. So we need to find a way to isolate the effects of dark matter. For that reason, another solution could be to study dark matter on subgalactic scales. At these scales, we have seen that the number density is different from model to model. And apart from that, the density profile is also different, as I will show you later. And we also know that at these scales, the halos are dark matter dominated, and baryons tend to not collapse and form galaxies. So these halos are dark. So having said that these are dark, how can we observe them? We observe galaxies because we see light. But if these halos do not have galaxies there, and have some gas that is not too bright, it's faint, then how can we detect them? Okay, this is the question. We have an idea. The idea is to use the strong lensing effect in order to detect them. Although they are dark, they are compact enough. They have a mass. Dark matter has mass. So according to the general relativity, it bends the light, a photon, when it passes close to the dark halo. So we can use a strong gravitational lensing, which is the light that passes by, which is the effect according to which when light passes by a massive object, its trajectory gets deflected. So what are the consequences of this effect? If you have a source, a background source here that emits radiation at different directions, then some photons that will follow some paths that move close to the line of sight, which is the line that connects the observer with the source, and we have a main deflector, a deflector in the foreground deflector, a lens in between the source and the observer, then photons that will follow different paths will be deflected and arrive at the Earth. This will produce lensed images, two idols or more, or multiple idols of the same source on the sky, but at different locations. So if you know that there is only one source, and if you can prove that these images are actually the same source, then you can measure the angular separation of the sky. And apart from that, if the source exhibits high intrinsic variability and emits pulses, then the arrival time of the pulses on the detector will be different. So we can also measure time delays because of the fact that the paths are different. Both of these observables, the angular separation of images and the time delay, can be used to infer the mass of the lens. So if you know that there is a source, and if you know that the lensed images that you get, are because of the strong lensing, and you don't see anything in between, then you know that there must be something compact that produces this deflection, this strong lensing, these multiple images of the same sort. And I will skip it because I think we don't have time. And I will proceed to the SMILE project. Yeah. So the SMILE project is a search for gravitational lens system on milliarc-second scales. So the SMILE project will exploit the strong gravitational lensing effect to search for dark or whatever can act as a strong lens, and we cannot see it. It will use high-resolution VLBI data, very long baseline interferometry data, in order to be able to go down to milliarc-second scales, resolution of the sky. And the data set is a large and complete sample of almost 5,000 compact radio active galaxies. This project is hosted by our institute, and it's currently ongoing. So if you want to learn more, you can either visit our site or come and talk to us. So why we want to use SMILE? SMILE is a probe will probe lensed images with angular separation of the order of milliarc seconds. This angular separation, this scale of angular separation, is produced by lens masses by lens masses which are between 10 to the 6 and 10 to the 9 solar masses. And this mass scale, as I explained you earlier, is quite important for dark matter scenarios since they exhibit different behaviors at this scale, this mass scale. For example, the number density is different from model to model. So given that the upcoming results of the SMILE will reveal the fraction of lens sources in the source sample, we can test the possibility that the compact object, the lens, is a dark matter halo. So if we manage to calculate in some way the expectation value of detected milli-lenses in the SMILE source sample for different dark matter models, then we can compare it with the observable, with the fraction of lens sources in the SMILE, and make inference towards the nature of dark matter. In order to do so, we developed a method which is based on the lensing optical depth, and I will explain you in a couple of minutes from now. But let's remind ourselves, what is the optical depth? If we have an incident, a light beam that hits on a slab of which has some absorbers uniformly distributed of number density n and cross section sigma, then the optical depth is the multiplication of the number density times the cross section times the length, the transverse length. In a similar fashion, we can define the milli-lensing optical depth, and I say milli-lensing because we are interested for lens images which have angular separations or angular separation of the order of milliseconds, and we can define this milli-lensing optical depth as we do in astrophysics. We integrate along the path of the photon, and instead of a cross section, we use the lensing cross section, which depends on the characteristics of the halo. As a number density, we can use the number density of lenses, which is related to the number density of halos, because we assume that the lens is a halo, not the whole halo, but a fraction of its mass. I will show you later. The path, as regards the path, we know that we can probe the cosmology, the cosmological model, but we decided to fix the cosmological model to be the concordance one and focus on the effects of the dark matter halos. The milli-lensing optical depth, as I told you, is related to the number density of halos and to the geometry of the lens, to the internal mass distribution of dark matter inside the halo. So if these two, if the density profile and the number density of halos is different from model to model, then we expect that all this expression here will be different. So it will differ from model to model. Now, as regards the abundance of dark matter halos, we can use either analytical works like the Preceptor one to model the number density abundance of halos in the field, or fits that have been derived from n-body simulations, such as the one of Lovell et al., which usually offer this kind of fits. Actually, these fits are the number density, for example, of the warm dark matter halo as a function of the cold dark matter one, and an extra term which encodes the difference between the two number densities. It's worth noting that if you go at large scales, that is, if the mass is greater than this parameter here, then half mode mass, then this term vanishes and the two number densities are identical. But if you go below this characteristic mass scale, then this term actually forces the number density of the warm dark matter halo to be suppressed, because these two parameters, which are fitting parameters of the simulations, their multiplication is negative, and therefore this term will result in something that makes this term smaller than 1. And as you go to much lower masses than the half mode mass, this quantity here vanishes with respect to the colder mass. In our study, we selected to test the warm dark matter scenario with mass 3.3 keV, which is related to the half mode mass, and predicts a half mode mass, which is roughly equal to 2 times 10 to the 8 solar masses. In order to show you the difference between these number densities, I have created this plot here, which is the number density multiplied by m squared, just for illustration purposes, as a function of the mass. The solid lines are referring to the cold dark matter scenario, while the dashed lines are referring to the warm dark matter scenario. At large scale, they are identical, while below 10 to the 9 solar masses, there is a cutoff in the warm dark matter scenario because of the free streaming that we discussed in the beginning. We cannot have small halos in a warm dark matter like scenario. But if it's not clear what's the difference from this plot, let's try to sample from this distribution dark matter halos. I have used the PyHalo package, which was developed by Daniel Gilman, and I sampled different dark matter halos that follow from this distribution, from this dark matter mass, the mass function halos. Larger bubbles correspond to higher masses, while the smaller one correspond to smaller masses. As you can see, in this cone that I sampled, within which I sampled dark matter halos, you can see that there are much more smaller halos. However, in the warm dark matter scenario, you can see much less. You don't really see too many small halos because of the suppression on the number density. So you expect that there are much less dark matter halos of low mass with respect to the one in the cold dark matter. Therefore, the number density of the deflectors is different, and as a result, the optical depth could be different. But apart from that, we do care about how compact is the halo, how compact is the lens, because in order to have a strong lensing event, the deflector must be compact enough so as to be able to bend light strongly and produce multiple images. This parameter, this quantity, depends strongly on the density profile of halos. At different dark matter scenarios, the density profiles are quite different. For example, the black solid line, which is the prediction for the cold dark matter scenario, predicts a cusp at the center, and the cold dark matter shows the similar behavior, but it tends to be, the mass distribution tends to be more extended and less concentrated at the center. This has to do with the C parameter, the concentration parameter, that is a parameter of the Navarro-Frank-White profile that can well describe this kind of halos. And the less the concentration is, the less the mass is concentrated at the center. For warm dark matter halos in general, this C parameter is different, and this C parameter dictates whether the halo is compact enough or not. And as I will show you later, it dictates whether the halo can act as a gravitational lens, strong gravitational lens, or not. Now, in the self-interacting scenario one, the predictions are in favor of a core, as I showed you in the beginning. So these kind of halos are well described by a core-like profile, and a typical one is the Berger profile. But according to the strong lensing theory, in order for a halo to be able to act as a lens, its surface mass density must exceed a critical threshold, a critical value. And because it cannot be achieved in the whole halo, only a fraction of the halo will act as a milli-lens. To illustrate this, assume that you have a sphere and the mass is distributed inside of it according to density profile. In the inner region, you expect the mass to be more compact, the density to be higher, as the density profiles show you. So you expect there the projected mass density, surface mass density, to have higher values. Therefore, if in the inner region the surface mass density is high enough, then this small inner region can act as a milli-lens, as a lens in general, but in our case as a milli-lens because we focus on this from the mass scale of our interest. The surface mass density is simply an integration of the density profile along the line of sight, and the effective threshold is a value which is on the order of 10 to the 9 solar masses per kiloparsec squares if the relative positions of the lens with respect to the observer and the source with respect to the lens are comparable. So if we solve this equation here, so if we equate the surface mass density with this effective threshold, then we can get an expression which relates the mass of the lens, which fraction of mass of the halo can act as a lens with respect to the total mass of the halo. So, since the density profile is different, we expect this relation between the relation between the lens mass and the halo mass to be different from model to model. And this impacts this expression here, the number density of lenses, since it is proportional to the number density of halos, but you also have to multiply by the derivative of the halo mass with respect to the lens mass. And this depends on the solutions that you get from this expression here numerically. So since the optical depth depends both on the density profile and the abundance of halos, we expect it to vary remarkably from model to model. In order to demonstrate that, we computed the lensing optical depth for 4 different dark matter models. The first model that we tested is the cold dark matter one, which is based on n-body simulations, and the density profile is given by the NFW. The concentration parameter is related to the mass, and we get the concentration mass relation from n-body simulations. As regards the abundance of halos, we use the Presefter mass function, which offers an analytical expression, an analytical form. Apart from that, we test another cold dark matter scenario, which is based on observations. The profile that describes the internal mass distribution is the same as the one we use here, but we now use a different concentration mass relation. The concentration parameter, which is a major parameter of the NFW profile, depends on the mass. And this concentration mass relation that we use in this scenario predicts a concentration mass relation that is much steeper. So at low masses, we expect the concentration to be higher, and therefore these halos are expected, are modeled to be more compact with respect to this one. So we want to test if the concentration mass relation, its slope, can lead to different results as regards the lensing, the strong lens. Apart from that, we test the self-interacting dark matter scenario, but we assume that the core collapses because we found that if the self-interacting scenario is in an expansion phase, I will not explain what the expansion phase means for now, but let's say that if it is described by a core at the center, then it cannot really achieve higher surface mass density values in order to act as a strong lens. But because we want to test this very interesting scenario, which is the core collapse scenario for self-interacting dark matter, which might explain the origin of supermassive black holes at high redshift, we consider that the inner region collapses, the inner region of the halo collapses, forming a compact object at the center. In order to model its abundance, because we don't have works that predict the number density of this self-interacting dark matter halo's core collapse, we use the Presefter mass function. And lastly, we tested the warm dark matter scenario, in which the rest mass of the warm dark matter particle is 3.3 keV. And in order to obtain a concentration mass relation and model the profile, the density profile, and we used results from simulations. As regards the number density, we use the one that I showed you earlier, and I show you also the plot, how the number density differs from the cold dark matter perception. So, what are we see that in the cold dark matter A, B, and warm dark matter D scenario, the NFW profile describes the internal mass distribution. So if they have the same density profile, why we expect them to be different? As I told you, the concentration mass relation is different from model to model, and therefore how compact the mass will be at the center, how concentrated the mass will be at the center, depends on how large is the concentration parameter. For the B scenario, where we use a steeper concentration mass relation, we have this curve here. For the A scenario, we have this one, while for the warm dark matter, have this one. And as you can see, the concentration mass relation tends to be smaller than the cold dark matter one, which justifies actually the result, the figure that I showed you earlier, where the mass in the warm dark matter halo is less concentrated. So using our method, using this formula here, we can calculate the milli-lensing optical depth as a function of the redshift of a source for these 4 different dark matter scenarios. And in this plot, we have done this calculation, and in this plot, I show you the result. The milli-lensing optical depth is plotted as a function of the source of the redshift. As you can see, the one dark matter D scenario predicts the lowest values of the milli-lensing optical depth, and this is this red dust curve here. While for the cold dark matter alpha A scenario, we get a similar behavior, but the lensing optical depth is a bit larger. However, when we use the steeper concentration mass relation in the B scenario, with which we allow the dark matter to be concentrated at the center of the halo, we expect the halo to be more effective when it comes to stronger milli-lensing. So we get this behavior here, in which the milli-lensing optical depth is much higher than the one for the cold dark matter A scenario, in which the concentration parameter is lower and therefore the mass is less concentrated at the center. And in the extreme case of the core collapse self-interacting scenario, we get the lowest values of the milli-lensing optical depth. This figure demonstrates that for different models, we get different probabilities to get a milli-lensing event, given that we have a source at redshift ZS. So how can we go from this result to the observable of the SMILE product? Actually, if we use this formula here, we can calculate the expectation value of detecting milli-lenses for different dark matter models by summing, by marginalizing over the redshift distribution of the source. And since in this plot, you can see that the milli-lensing optical depth is well below 1, we can approximate this formula by this one here. So the expectation value of detecting milli-lenses is actually a summation over the lensing optical depth for all sources in the SMILE source sample. Since it depends on the redshift, it depends on the redshift distribution. In the SMILE project, we have redshift information for the 2/3 of the sources, while we are currently missing the redshift information for the rest of them, for the approximately 1/3. In this figure here, the blue line refers to the redshift distribution of the sources of known redshift, and because we don't really have any information about the redshift distribution of the sources of unknown redshift, we made the conservative choice to assume that they have the similar redshift distribution. So in doing so, we calculated the expectation value of milli-lensing detected milli-lenses in the source sample of SMILE for these 4 different dark matter scenarios. As you can see, the cold dark matter A and the warm dark matter D scenario predict 0 milli-lenses because the milli-lensing optical depth we saw that it vanished. In contrast, the cold dark matter B scenario predicts 1 milli-lens within a range of uncertainty, and the extreme scenario of the core collapse self-interacting predicts to 13 milli-lenses, almost 13 milli-lenses. As at least this plot can convince me that different dark matter scenarios will predict quite different expectation value of detected milli-lenses. So if we combine these expectation values, theoretically expected values of detected milli-lenses, with the observable, then we can guide ourselves, we can figure out whether we should go towards models that predict halos that have the mass more concentrated at the center, or not. For example, if we detect some milli-lenses with a SMILE project, then we know that the warm dark matter scenario can be ruled out, and the same can be argued for the cold dark matter scenario, in which the concentration mass relation is very shallow, which means that the concentration parameter in low mass dark matter halos is not too large. But because at different cold dark matter scenarios we get different results, because we just change the concentration mass relation, we can infer that by milli-lensing observations we can constrain or infer the slope of the concentration mass relation, how steep the concentration mass relation is, down to subgalactic scales, which cannot be done by the standard observations because the only way to go down at these scales, at least currently, is the strong gravitational lensing, and actually the strong gravitational milli-lensing, because once we go down to this mass scales, we talk about milli-arc-second separation. So in this final couple of minutes, I want to talk about the sources of uncertainty in our work. First of all, the redshift distribution of the 1/3 of sources has not been determined yet, and therefore we have to take into account. We have to obtain redshift formation for all sources that the SMILE project is going to analyze, because the expectation value depends on the redshift distribution. Apart from that, we didn't account for the effect of baryons, if any, but someone has to quantify it, on the overall strong lensing. And lastly, we didn't take into account the possibility that supermassive black holes that are hosted by halos can act as a lens and contribute to the overall strong lensing effect. So let me draw my conclusions by summarizing what we have found. We have shown that the source sample included in the SMILE project is sufficiently large to enable inferences about the nature of dark matter. We have shown that warm dark matter halos are highly unlikely to act as milli-lenses and produce lensing events in the source SMILE sample. And we also have demonstrated that self-interacting dark matter halos can act as strong lenses only in the case where the core collapses. And finally, we have found out that the ability of core dark matter subgalactic halos to act as milli-lenses depends strongly on the concentration mass relation, on the steepness of the concentration mass relation, and therefore we can really constrain this concentration mass relation through milli-lensing observations. So, to sum up, we know that the dark matter identity remains an enigma, perhaps the greatest in physics today, but through milli-lensing, we have good reasons to believe that we can really make considerable progress towards the identification of the dark matter nature. So this work, in this work, I had many people that helped me and supported me. And so I would like to express my deepest gratitude to my supervisors, Professor Valiki Pavlidou and Dr. Carolina Casadio. I also want to thank our collaborators, Professor Kostas and the members of the SMILE group, who helped me a lot and provide me with constructive feedback throughout my work. I also want to thank Professor George Silk, Dr. Dan Gilman, and Professor Haibo Yu for fruitful discussions that we had, and that which really helped me to complete this work. And I also have to say that we are currently trying with Professor George Silk to estimate the effect of supermassive black holes on the strong lensing event and answer the question whether supermassive black holes contribute significantly to the strong lensing that is produced by halos or not. And with Daniel Gilman, we want to extend our work and go through simulations in order to be able, first of all, to be more robust, and second of all, to search the whole parameter space and test a bunch of different dark matter scenarios. I also want to thank my mentor, Professor Nick Hilafis, since he was an endless source of inspiration for me all these years. And lastly, I want to thank the University of Crete, the Institute of Astrophysics at Forth, my office mates and the grad students of EA Forth for creating a healthy working environment. And with them, I had many pleasant breaks, which allow me to recharge my batteries. And also my family, my friends, and so thank you for your attention. Yeah.
On the final plot, the one with the number.
Yeah.
The error bars, what do they include?
Okay, that's a good question. Our first thought was that since they are events, the error bars are given by a Poisson, are Poisson-like errors. However, one has to do this calculation more robustly and include the scatter on the concentration mass relation and other sources of uncertainty that are included in our calculation and redo this calculation. We plan to do so by going through simulations, which are more accurate. But at least we have shown that different scenarios predict different expectation values, and the milli-lensing observations have strong discriminatory power. Yes. Vincent.
Vincent, thank you.
As far as I understood, you fixed the cosmology.
Yes.
In your estimate of the,
Mm-hmm.
do you have any idea on the impact of releasing parameters? If you change the dark matter issue, you may change.
Yeah, if you change the amount of dark matter, then of course, if you change the how dark matter will have the omega matter, then of course everything changes because the number density of halos changes as it scales with the mass density, with the matter density of the universe, and therefore we expect if we increase the omega matter to enhance the probability against a milli-lensing effect because of the fact that the number density will be greater. However, you cannot really play a lot with omega matter because we have strong indications that it's roughly equal to 0.3.
Because you can play with sigma.
Yes.
Can you go to the figure, to the previous slide? Not the previous one.
The lensing, the optical depth.
Of the models, for models and
Yes.
yeah, this one.
Mm-hmm.
So the question is not exactly related with what you did, but from reading the literature, how well do we know the mass concentration relation and from observation?
Yeah.
What's the status?
Okay.
Suppose if we see the green what is it, dust dot?
Yeah, dot dust line.
Self-interacting dark matter
No,
line.
the cold dark matter one, which has a steeper concentration.
Yeah.
Yes.
But one guess that you can make them look very similar if you play.
To look similar, which one? This one with this?
No, these two are out of the question.
These two.
Yes, exactly.
Yes, actually, if you use a much steeper concentration mass relation, and we did that, you get almost the same milli-lensing optical depth because the total mass inside the halo must be conserved. So if you allow the core, the mass which is within the core, to be contracted and accumulate at the center, then the density profile vanishes at larger scales, and therefore only the inner region is the one that acts as a milli-lens. And either you assume that the whole inner region is accumulated at the center, or if you assume that the concentration is too high, then actually it's almost the same. Because again, you get compact inner regions and something that is very.
That's why I asked you how well do we know.
Yes. Okay. Actually,
I can fix the mass.
yes. Then we can.
Then I don't have to consider the
Exactly.
nature of that matter.
Yes. Well, the concentration mass relation can be constrained from galactic scales and above, and this is what we now know. But you don't really know what happens below this scale. In this figure here, you can see that these three lines converge on galaxy cluster scales at the same concentration mass relation. The scatter of data there is huge. So you cannot really obtain a robust fit and extrapolate down to some galactic scales in order to find the concentration mass relation. And this is the reason why we used, so much different concentration mass relations to see if we can go down on these scales with milli-lensing. Because you cannot constrain the concentration mass relation below galactic scales because you cannot observe these halos. But with milli-lensing, you can. And actually, the concentration mass relation plays an important role on how effective these halos are. Yes.
So the thing is the following: you have to choose, right?
Yes.
You either measure the concentration mass relation, or if you make a discussion on the nature of that matter, but you cannot have both. right?
Why?
Right now.
There are models.
Because you should know the concentration mass relation observation.
You know it here, but who tells you that it's extrapolated and has this form down to subgalactic scales? It's an assumption.
Let's
Hmm.
So we use dark matter abundances without concentration concentration, but simulations cannot.
Yes. Yes.
Yeah.
Very nice presentation. A very nice project. Given that the cold dark matter is one of the cold dark matter was really exactly 0 milli-lensing sample size. Do you know what kind of sample size you need to distinguish between these two?
Yeah, I can answer your question roughly because we haven't tested for larger samples, but here you have all the information. You have the milli-lensing optical depth. So let's say for these scenarios, the mean value of the optical depth is 10 to the minus 5. Or let's overestimate it and go to 10 to the minus 4. Then, since the expectation value of detected milli-lenses is a summation over the total amount of sources, then if you assume that all optical depths are equal to 10 to the minus 4, then you need at least 10 to the 4 sources in order to get at least one milli-lensing event. So we need at least to go an order of magnitude higher when it comes to how large the source sample is in order to be able to also test these models. I don't know, does it answer your question?
Any other question? If not, fun as that was, I can figure it out. So I will ask the audience to give us, and then question for